Hello everyone, my name is Simon Häger and I'm a PhD student at the Communication Networks Institute at TU Dortmund University in Germany. Today I present a new method for measuring of fine-grained 3D motions with high accuracy. For this work we were joined by fellow researchers from the Fraunhofer IEG in Bochum, Germany. In this talk we first motivate our work based on current and planned developments in the field of mobile radio networks and ground motion and infrastructure monitoring systems. Second, we will briefly introduce the relevant basics for this work. Afterwards, we introduce our novel architecture for environmental sensing and derive its core novelty, a new motion metering method. Thereafter, the evaluation methodology and scenarios are explained. We then analyze the results, draw conclusions, and last, provide an outlook on future works. In preliminary 6G discussions, introduction of radio and particularly of radar-based sensing services has emerged as a hot topic, among other things. The aim is to make networks perceptible of its surroundings, for example, in order to enhance the network operation itself. However, the key incentive for network operators are the many novel use cases which open up new revenue streams. In the past, many works have focused on radio-based services operating at traditional RF frequencies. Nowadays, integration of radar-like sensing has become a key area of research due to the planned use of mmWave and terahertz frequencies, which offer large bandwidth, high time resolution, and adjustable directional antennas for high accuracy sensing. But it will be several years of development before this type of service generates new revenues for network operators. Current systems for ground motion and infrastructure monitoring require expensive equipment and expert staff, which is prohibitive to many small-sized and funded applications. However, such technology is crucial for public safety and disaster relief efforts. Due to these costs, deployment of such systems is not where it could be. This should not be a luxury. We have therefore identified a need for a complementary system which is based on deploying low-cost sensors that may be deployed densely and with guarantees for reliable communication at low latencies. Additionally, such a system should be able to operate intelligently. Based on these requirements, it was clear to us that well-established 5G infrastructure can serve as the backbone of such a system, with commercial off-the-shelf user-side devices available all around the globe. In this work, we show that 5G mmWave communication links can be used for ground motion and infrastructure monitoring by means of a novel radio-based sensing concept which leverages the antenna beam-based operation principle at the mmWave domain. This shows that innovative sensing services could already be introduced in the coming years running on current generation networks. The move to mmWave frequencies, meaning frequencies greater than 24 GHz, comes with challenging propagation characteristics. To enable robust communication and sufficient range, large antenna arrays and beamforming technology have to be used. The resulting antenna beams must be aligned precisely all the time. So-called beam training handles initial access of the user equipment to the network. By means of exhaustive testing of all beam combinations, available link opportunities are identified and the most suitable one, typically the line of sight path, is selected for communication. Afterwards, beam tracking and switching schemes realign the beams, for example, if the current beam is outdated due to user mobility or when it is blocked due to ambient mobility. Yet this last category of algorithms is not yet mature. Naturally, one should ponder the question whether 5G mmWave at this point in time is sufficient for the intended infrastructure and ground motion monitoring services, which we explain on the next slide. We find the lack of major beam tracking and switching algorithms is not a problem if sensors are mounted to walls and are therefore stationary, in particular if they are mounted at sufficient height where ambient mobility cannot interfere. Additionally, these prerequisites align well with fixed wireless access deployments in which UEs are primarily deployed to provide wireless broadband access. On the left side, we show such a scenario where a mmWave UE is mounted to a building and monitors for different types of motion as shown on the right side. For example, winds-induced movement to large buildings such as skyscrapers. By tracking this movement, the structural stability of the property may be assessed. Movements are typically in the range of up to several centimeters with frequencies below 1 Hz. In current and former coal mining regions, but also where water, gas, or oil is extracted, so-called subsidence occurs. Subsidence is characterized by sudden sinking or gradual downward settling of the ground with little to no horizontal motion. A typical value for gradual sinking is in the range of about 2 to 3 millimeters per year, such that the human eye can detect the resulting cracks in infrastructure. More noticeable are earthquakes, which must be detected as soon as possible, for example to shut down systems safely. For these purposes, movements with frequencies of up to 1 kHz must be detected, although the most significant energy lies within the frequencies up to 20 Hz. There are further sources for fine-grained motions, such as goods traffic and construction. These act as a source of noise during studies of the subsurface medium. Dense sensor networks could detect these and therefore aid in the analysis of subsurface rock formation properties. As we have shown, there are several safety-critical and research-related use cases for monitoring of fine-grained movements of ground and infrastructure. All of these come with different requirements which can be served by 5G, as we show in this work. With this background, we now introduce the novel system architecture and measurement technique. 5G serves as the backbone by enabling reuse of existing infrastructure, easy access to compatible UEs acting as sensors, reliable low-latency communication, and intelligence, as our architectural overview shows. The main contribution of this paper is a novel measurement technique for detection and reconstruction of fine-grained 3D motions, which we will discuss in detail later on. Typical 5G devices, such as smartphones, also come with several other sensors on board, for example accelerometers, gyroscopes, or GNSS receivers. This data may be fused for better performance. The previous two components of our architecture provide larger data sets of complex data from different sensors and platforms compared to conventional methods. This results in complexities difficult to solve by numerical techniques alone. The use of AI methods could have a tremendous enabling impact on analyzing the obtained data. By embedding such a method in the mobile edge cloud of the 5G network, fast and efficient computation may be realized, thus allowing for quicker and better informed decisions. We now move to the heart of our work. We start with the channel state information estimation-based block. Small movements impact the signal phase of the last received signal compared to a previous received reference signal. This information will be contained in the mmWave channel estimates h-shift and href for time instances T2 and T1. In this work, we leverage the channel estimates of the channel state information reference signal CSIRS, which is transmitted by the base station to a specific UE by leveraging n equally spaced subcarriers. Hence, the movement can first be estimated on each carrier individually after unwrapping of phase difference vector delta. The formula for the movement estimation per used subcarrier compares the fraction of phase change to the used wavelength to derive the corresponding movement. Last, by averaging the movement estimate of each subcarrier, a scalar estimate is acquired. At this point, we have to note that the movement estimate only corresponds to the movement along the axis of the incident electromagnetic wave. Therefore, orthogonal movement components cannot be detected. For compensation, we add a novel beam-based component to our motion measurement technique. Our first idea for this was to estimate the movement components by considering the mounted mmWave UEs steering angles phi and theta, which correspond to the azimuth and elevation angles. The formula, however, couples the movement components based on its angles. This may introduce error. Nonetheless, we provide a method to get an initial estimate of the 3D movement with just a single link opportunity. However, beam training also finds other link opportunities which could be exploited in addition to improve the performance. These link opportunities could be well-separated propagation paths to the radio network. Yet this is not in the hand of the user compared to deploying additional devices, which we therefore consider in this work. If U sensors are deployed, measurements are available along U different propagation paths. By means of repurposing a scheme from the radar domain, we reconstruct the true 3D movement in 3 steps. The first step, 2 mutually orthonormal vectors are determined for each vector RU. In the second step, a linear equation system is set up. On the right side, we show its structure for deployment of 3 UEs. Using the inverse of A, column vector C is determined. In case of large deployments, the pseudo-inverse finds the least square solution. The elements of vector C describe the orthogonal movement components which were not detected by the measurements, but may now be detected by merging all measurements and the beam orientation information. Last, with help of vector C, U 3D movements are reconstructed. Considering system scalability, the mean of these is taken as the final estimate of the true 3D displacement. In the following, we explain how we evaluate this new measurement technique. Our evaluation is based on ray tracing data from ANSYS HFSS, which allows us to model mmWave channels in frequency domain under fine-grained parameterized mobility. The channels are simulated in the band from 26.5 to 26.9 GHz. For 60 kHz subcarrier spacing deployment with a CSIRS density of 1, phase measurements will be conducted on 555 subcarriers with 720 kHz separation. The same software is used to simulate the antenna pattern by modeling a planar 8x8 antenna array. The resulting highly directional beam pattern, along with its key parameters for the boresight direction, are shown on the right side. In the two different deployment scenarios that we introduce on the following slides, we have mounted the base station's antenna array to a building at a typical height of 10 meters. In order to study the performance for different deployments, up to 10 user devices will be deployed. For simplicity, these are mounted to the same property with a spacing of about 1 meter. The first scenario, as shown on the left side, is about measuring horizontal, wind and seismicity-induced movements of a skyscraper. The movement x-shift goes from 0 to 5 mm in steps of 1 mm. As reference position serves x-shift equal to 0 mm, as the beams were aligned perfectly for this case, with an azimuth angle of 45 degrees and an elevation angle of about -78.8 degrees. On the right side, we show the case that the customer deploys up to 9 UEs to monitor the skyscraper. We note that UE1 in the middle corresponds to the UE depicted in the figure on the left side, for which we provided the beam alignment. The other 8 UEs have different, although similar beam orientations. The second scenario is about measuring the subsidence caused sinking of a house in a former mining region. The movement z-shift goes from 0 to -5 mm in steps of 1 mm. Again, the beams were aligned perfectly. On the right side, we now show the case that the customer deploys up to 10 UEs. We changed the mounting of the UEs within this scenario in order not to mount the UEs too close to the ground, where the connections could easily be obstructed by ambient mobility. During the evaluation of the performance of the proposed measurement technique, we investigate the incurred relative error between measured movement vector and the true movement vector. This relative error is a measure for the Euclidean estimation error in 3D space normalized to the length of the true movement. For example, a relative error of 1, that is 0 dB, means that the estimation error is as large as the movement itself. This indicates bad performance. On the other side, a relative error of -20 dB would mean that the 3D movement estimation error is just 1% of the overall movement, thus indicating high accuracy. Throughout our analysis, we also consider deployments with less than 9 to 10 UEs. Analyzing all possible deployment constellations in detail exceeds the scope of this work, hence we select those minimizing the condition number of matrix A for a given number of deployed UEs. This decision is based on the relative error limiting characteristic as follows. If matrix A with minimal condition number is used in the linear equation system B equal to A times C, which is being solved in the movement vector estimation part, the estimate of vector C will be least volatile to little changes of vector B, which contains the phase-based movement estimates. With this evaluation setup, we can finally study the results, starting with scenario 1. First, we compare the measured to the true movement using the coupled formula for reconstruction of the UE movement. While a single UE suffices, a significant error is incurred for all movement components. Next, we deploy 3, 4, 6 and 9 UEs. It can easily be seen that the estimates are much closer to the true movement. We now take a look at the relative error for the single UE movement measurement. With a mean relative error of about -1.3 dB, the incurred error is nearly the size of the movement. We now further take a look at the incurred relative error for deployments with 3 to 9 UEs, again showing the results of the UE constellations which minimize the condition number. There are several things that can be seen. First of all, with the relative error being smaller than -15 dB in all cases, measurement accuracy is better than 32 micrometer. In some cases, incurred relative error are smaller than -20 dB, corresponding to a 3D movement reconstruction error below 10 micrometer. This is likely due to the impact of multipath propagation. All of this shows that our novel mmWave radio-based sensing algorithm can indeed measure small-scale movements with high accuracy. Last, we take a look on the distribution of mean relative error over all possible UE constellations. Naturally, there are more combinations of selecting 3 out of 9 UEs than, for example, selecting 6 out of 9 UEs. This may be seen for the curve of 9 UEs, as there is only one possible combination. Nonetheless, it can easily be seen that, on average, increased numbers of participating mmWave UEs improves the measurement accuracy. For large deployments, sub-10 micrometer measurement errors can be achieved. In some cases, micrometer level accuracy is approached. On the other side of things, minimal deployments of 3 UEs sometimes perform as bad as when using just a single UE. This is due to cases where the condition number was very bad, such that the algorithm enforced use of pseudo-inverse to avoid even worse results. Nonetheless, even if more than 3 UEs are deployed, some mounting combinations perform bad. This shows that the mounting of several UEs cannot be conducted arbitrarily, but should be planned beforehand. Considering the cases where near 1 micrometer accuracy is achieved, this also shows that minimizing the condition number is not necessarily suitable for this. In the following, we briefly study the results for the second scenario, where an even better accuracy is achieved. Within this scenario, sub-10 micrometer accuracy is achieved on average for each deployment size. Actually, at least 96.2% of all deployments with at least 4 UEs pass this threshold. This contrasts the mean relative error of -7.5 dB when just using UE1. A reason for this performance enhancement could be the smaller scenario size, which translates to increased azimuth and elevation ranges, which being covered by the UEs. In turn, this then supplies the movement vector estimation algorithm with more clear information on orthogonal movement components. However, it must also be noted that the gain of adding UEs has shrinked as the curves are spaced more tightly than in the former scenario. Thus, deployments of fewer UEs are indeed feasible, in particular if their placement has been optimized beforehand. At last, we summarize the contribution and findings of our work. Sensing use cases envisioned for 6G are far from realizable right now. In contrast, this work has introduced the sustainable secondary use of 5G mmWave for ground motion sensing and infrastructure monitoring for research and safety purposes by using commercial off-the-shelf UEs. By means of measuring CSI phase changes and by beam orientation information, fine-grained movements can be reconstructed. Our ray tracing-based experience verified that the achievable 3D movement tracking error is well below 10 micrometer. Our ongoing work studies the system performance under error sources such as beam misalignments and tries to optimize the mounting of the UEs. Future work will integrate and evaluate the use of onboard sensor data and AI methods. Thank you very much for your attention. I'm looking forward to answering your questions.